Okay, welcome back. Sorry, let me just get myself geared up here. Get my holster strapped on. All right. So last time, oh, sorry, before does this belong to anybody? That's not there. Okay, somebody's audio recorder, and it's still recording, so they get 2 lectures for the price of 1. So last time we didn't quite get finished. Actually, we didn't at all get finished talking about anomalies that can't be explained by the expected utility theory of Daniel Bernoulli and von Neumann and Morgenstern. So we're going to finish up with that, and what I'm doing here is I'm building up the components of prospect theory, sort of anomaly by anomaly. So we'll finish that up, and then I'll show you so what I'm doing is I'm building up a positive model, right? Anomalies are positive problems. They're things that the model can't predict properly, can't explain. And then, as I want to do, I'll show you a big fat normative problem, which is the way that the Allais paradox violates rationality under the expected utility theory. And then we'll talk a little bit about some applications, and hopefully we'll get to number 3, which is a really cool paper that you are required to read about a TV game show, which turns out to be a televised economic experiment, though probably the producers didn't realize that. I will just say, so there's 2 assigned readings for this week. There's a prospect theory paper, and then there's this deal, no deal paper. Worry much more about the prospect theory paper. The deal, no deal paper, I actually sort of tossed up whether or not to just make it non-required, but I think it's fun. It is very closely related actually to this week's problem set, the first part of this week's problem set. So if there winds up being anything on the exam related to the deal, no deal paper, it will be closely related to the stuff that I'm going to hopefully show you today and the stuff that's on the problem set. So I'm not going to throw you any kind of curveballs from that paper. Okay. So last time, building up prospect theory, 1 anomaly at a time. The first anomaly what we looked at was the rejection of small stakes better than fair gambles. And I hope that I convinced you that the kinds of rejections, would you accept a bet of where you get 550 with probability 1/2, or you lose 500 with probability 1/2, can't be explained by expected utility theory. And so we said, well, therefore, it must be the case that the instantaneous utility function that people are using to evaluate outcomes must be kinked at a reference point with loss aversion, just like we've seen in non-risky situations. And then we looked at another anomaly, which is the reflection effect, that people seem to go from being risk-averse to risk-neutral when you change the outcomes from being gains to losses. From not risk-averse to risk-neutral, risk-averse to risk-seeking. That people typically, by and large, seem to be risk-averse over gains and risk-seeking over losses. Now, somebody towards the end of that asked me, or in the middle of that said, how does problem number 4 prove that you're risk-averse? Was that you? I'm not going to answer the question during lecture, but I can give you an answer after class if you want. Actually, you'll probably get the answer during the course of this lecture, because that problem's going to come up. Okay, so we said, okay, this can't be explained. This reflection effect, that people's risk preference flip-flopping when the sign of the outcomes goes from positive to negative, can't be explained by expected utility theory with a wiggly utility function for a variety of reasons that we went over. And again, I hope I convinced you of that. And so if we have already concluded that the instantaneous utility function is some kinked loss aversion type of thing, then it must be the case that it's convex in losses and concave and gains. And so we came up with something like this. On your handout, my computer does something from time to time very bizarre, which is that it refuses to print some of my math. So you don't have those axis labels. So just stick those in so your handout is complete. I apologize. I literally have no idea why that happens. This is actually a cut and paste from the prospect theory paper. This is exactly what, in 1979, Kahneman and Tversky put forward. And it's not, I don't think that that's based on any actual mathematical function. I think they just drew it. But on B-Space, there's a follow-up, which is called Tversky and Kahneman, 1992, which is advances in prospect theory. And they've actually written down a mathematical function for a value function looks like this. And we're actually going to see a graph of it in the last slide today, because that's the 1992 Tversky and Kahneman value function mathematically is exactly what the deal, no deal paper uses. So you can see how this stuff builds on itself. Okay. So much for the instantaneous utility function, right? We think it's got to look like that, or something like that. Now let's talk about probability weighting. Right? One of the implicit assumptions of the expected utility theory, as put forward by von Neumann and Morgenstern, is that the probability weighting function, which we're going to follow Kahneman and Tversky and calling pi of p, right? P it represents the probability of a certain state of the world happening, and then the amount, the weight in expected utility that people put on a given probability is some function of that pi, and the implicit assumption in expected utility is that pi of p equals p. That people just use the probability straight up. Okay? And we're going to poke into that and see if that seems likely to be true. So here's the first probability weighting anomaly we're going to look at. Simultaneous lotteries and insurance. Now, we talked about this on the very first, I talked about it on the very first day of class, right? The thing that Milton Friedman was getting all wrapped around the axle about was the fact that expected utility theory has a hard time explaining the stylized fact that people simultaneously take out insurance on relatively unlikely high risk, high cost losses like your house burning down, and also buy lottery tickets, right? So both of these are sort of high stakes, small probability gambles. One in the negative domain, one in the positive domain. And so what we see when people simultaneously buy lottery tickets and take out insurance is that it looks like they're exhibiting big-time risk-seeking in gains and big-time risk aversion in losses, which is just the opposite of what I said a minute ago. Yeah? So now we're really in trouble. Because not only can this not be explained by expected utility theory, but it actually also can't be explained by the prospect theory value function. If this is the prospect theory value function, right, and I give you a lottery ticket, which is basically with probability 0.999999999, you're going to get nothing. And with 1 minus that, you're going to get some fantastic amount of money. Okay? Doesn't matter what the probabilities are if your probability weighting function is linear. If you're risk-averse, you're risk-averse, right? I mean, unless we think, but actually it's this, but then suddenly out here somewhere it does that. No, that's not, we just know that kind of explanation doesn't make sense, right? Because this is true for people at all wealth levels. And, okay, so it's actually not, that's not the issue here. Why couldn't it just be the case, right? Because if it just suddenly went like that, then you'd say, well, actually, this person is risk-seeking over that. But that's just not, it's not what we observe. It turns out it doesn't have to do with the size of the stakes and the shape of the value function. It has to do with what people are doing when there's a very small possibility of something, right? If I tell you, okay, with probability 0.99, we're going to just discuss some behavioral economics for the next 75 minutes, and then you're all going to get to go do the next thing, which hopefully is lunch. And with probability 0.001, we're going to die in a fire that will only affect this room, and we're all going to die. Raise your hand if you would leave. I would leave, right? So and I can make that probability a lot smaller, and you'd still all leave. Because it's just that we're impressed by these small probabilities. So this not only can't be explained by expected utility theory, it also can't be explained by the prospect theory value function. Okay. First, let me show you that, so Kahneman and Tversky actually sort of studied this and have some actual empirical evidence. They've gone from stylized facts, which is what Friedman and Savage were working with in 1948, to actual facts, at least based on their methodology. So here are two problems from the prospect theory paper that you're assigned to read. In problem 14, people are faced with a very small probability of a pretty sizable gain, yeah? Or $5, right? They have the same expected value, yes? So the fact that people are willing to take a very small probability chance on a gamble with the same expected utility as the $5 says that they're risk-seeking. That's what that means. If you make two gambles have the same expected value and one of them has a less than 1 probability, if one of them is certain and the other one is uncertain and they have the same expected value, and you take the uncertain one, that makes you risk-seeking by definition. So we can think of this as a lottery, right? And so people exhibit risk-seeking behavior, and quite a lot of them. So that this 5, that's like the ticket price of the lottery, essentially. And then 14 prime, they just multiply both sides of that by -1. So this is like you face a 1/10% chance of losing $5,000, and you can insure yourself against that by just paying a $5 premium. Okay, so this is insurance. And you can see that overwhelmingly people want the risky gamble, and they don't want the risky loss, the negative risk. And I think that they also say in the paper that 65 out of 100 people gave both of those answers. So there's a sizable majority of their subjects who are buying lottery tickets and insuring themselves against small risk losses. Okay, yes?
So back to your fire example, I think you also know that airplane crash is a really low probability. Does that mean that people who don't fly in airplanes do not exhibit this anomaly?
So your name is Diana, right? Diana's question is, we all know that flying on airplanes, like dying in an airplane crash is a very, very low probability, and yet we still do it. Does that mean that people who fly on airplanes don't exhibit this anomaly? It doesn't mean that they don't exhibit this anomaly. It does mean that the benefits to them of flying outweigh how they feel about even an inflated perception of the risk of crashing. Yeah. Okay. So this is the exact opposite of the, sorry, I haven't quite finished. That's risk averse. That's the opposite of the reflection effect. If the value function, v of x minus r, is concave in gains and convex in losses, then subjects must be overweighting the probabilities of these things happening. Yes? Oh, does this keep happening when the stakes get really, really, really big? So the question is, does this scale up? If you multiply by the outcomes by 1,000, you would take the 5,000. I don't know the answer to that question. I strongly suspect that I think that my response to that is going to be the same as my response to Diana's question, which is that I don't think that that would prove that you're not overweighting small probabilities. It would only tell us that if you're overweighting small probabilities, you are not doing so by enough to overcome your simultaneous risk aversion. Right? So we're saying that the value function is making you risk averse, and then your probability overweighting of this small probability is overcoming that risk aversion. So if I scale this up and that's no longer the case, that doesn't necessarily tell me that you're not overweighting small probabilities. Yeah. Okay. Let me do some math to convince you of this. So suppose that this is just the gains part, right? And here's v of x minus r. Suppose I stick in $5 there, $5 gain, and that's v of 5. Okay. What I want to know is, let me stick in 5,000. I know this is not the scale, but it doesn't matter. If I draw a straight line through that, okay, I'm going to have to move the 5,000. If I draw a straight line through that point, then the place where 5,000 intersects that line tells me the point 5,000 times v of 5. Yes? Sorry, 1,000 times v of 5. Because this is going out 1,000 times. Along a straight line, that point should also be going up 1,000 times. That's what a straight line does. This point, meanwhile, tells me v of 5,000. So if there's concavity in the value function in the realm of gains, then it must be the case that v of 5,000 is less than 1,000 times v of 5. Okay? By concavity, v of 5,000 is less than 1,000 times v of 5. Now we've already convinced ourselves that the value function is concave in the domain of gains, so we're just going to take that at face value. That means, just rearrange terms, that v of 5 divided by v of 5,000 is greater than 0.001. Does everybody get that? This so far has nothing to do with probabilities whatsoever. It just has to do with a simple mathematical fact that I'm pulling out of the concavity of the value function in the domain of gains. Now, by problem 14, up here, what I know is that the prospect theory expected utility of the gamble, which we write as pi of 0.001 times v of 5,000, right? That's the prospect theory value for that gamble, 5,000 with probability 0.001, is greater, at least for 72% of their subjects, than v of 5. Yeah? That's what that means. And that implies that pi of 0.001 is greater than v of 5 over v of 5,000. We just proved by concavity that that's greater than 0.001. So what we get here is that the weight people are placing on a probability of 0.001 is greater than 0.001. Okay? And you can do exactly the same math for problem 14 prime, and you'll get exactly the same result if you assume, as we've already demonstrated, that the value function is convex in losses. You'll get exactly the same result. And you might want to do that math because the more math you do, the better you feel. So this is some evidence to suggest that people overweight small probabilities. Yeah? Any questions about how we got that result? Okay. Now let's look at the flip side of the coin. This is the Allais paradox, and I'm sorry I don't know who Allais was, but he's an extremely famous, well, his name is, his paradox is famous. And paradoxically, he's not, but except because of his paradox. So what happens if we, so this is back to problem 4 of, problems 4 and 3, which were what we were wrestling with last time. Why does problem 4 represent risk aversion? What's going on here is we're going to take people's answers to these two problems, and we're going to see what those answers imply if we assume that the value function looks like this, and if we assume that the probability weighting function looks like this, is linear, right? Because this is the thing we're trying to bash on. Okay? If that's the case, if the probability weighting function is, actually we don't even really need to make any assumptions about the value function. We're just going to focus on the probability weighting function. If the probability weighting function is this, pi of p equals p, then what problem 4 tells us is that 0.2 times v of 4,000. Okay, I need to move this up a bit or I'm going to run into my next bullet point. Is greater than, right, because 65, for these 65 people who preferred this, that's greater than 0.25 times v of 3,000. Okay? And what problem 3 tells us is that 0.8 times v of 4,000 is less than v of 3,000, because over here in problem 3, people prefer the 3,000 for sure. Okay, the lovely thing, the whole point of making an assumption, a mathematically formal assumption about things like this, is that once we've represented mathematically what these preferences mean, we can then just manipulate them mathematically, and the statements should continue to be true, right? If the model, if we believe the model, then we ought to be able to do some math on these results and have the results still hold. So why can't I just multiply both sides of this math by 4? That would give me 0.8 v of 4,000 is greater than v of 3,000. Right? If the probability weighting function is linear, and people are evaluating their preferences for gambles according to some linear combination of some value function, it doesn't even matter what the value function is. Okay? Problem 4 suggests that people would prefer to take the 80% chance on 4,000, but we've seen that in problem 3 they actually don't. So this represents a contradiction, and that is the symbol for contradiction. So if you're doing a proof by contradiction, you put that little symbol at the point where you actually get the contradiction, and then you say QED. That symbol is fencing swords crossed, is what that is. It's a contradiction. Okay. So what seems to be going on here is this. We took problem 4, and we made both of the outcomes 4 times as likely. Yeah? We just scaled up the probabilities by a constant factor of 4. And apparently, when we made these things more likely by the same proportion, making one of them certain mattered more than making the other one just more probable. Right? So sometimes we talk in terms of people having a taste for possibilities instead of probabilities. Okay? When this thing goes from possible to certain, it seems to have a stronger impact on preferences than when the 4,000 goes from being somewhat unlikely to relatively likely. Okay? And what that suggests, so we call this the certainty effect, and it suggests that people are doing something very similar to overweighting small probabilities. In fact, we can reframe this so that it is conceptually identical to overweighting small probabilities, because we can say something like introducing a 1% chance that something nice won't happen matters more than increasing that probability from, say, 42% to 43%. Okay? So you can think of this certainty effect, that people like just that last little push from really, really quite likely to certain, more than the same increment of probability somewhere in the middle of the probability scale. So this is just, once again, both of these effects are just diminishing sensitivity at work. I'm going to show you this on a graph in 2 seconds, but go ahead. Oh, you think that these 65 who are saying they like this and these, like let's say that all of these 65 are in this 80. You're just saying, well, actually they were just really close to indifferent and they said, what the heck, I'll go this way on this one and this way on that one. So if you're indifferent between two things, how do you choose between them? What? Flip a coin. Okay, so if there's 65 of these people, why are they all flipping the coin the same way? Doesn't seem that likely. Doesn't seem that likely. It's a good catch. Good to see that. I'm glad that you're thinking in terms of the actual assumptions that we really genuinely make and what it really means to prefer one thing to another. But I think that story doesn't, it's not a super likely candidate for explaining these results. Okay, so let me show you what we think this means. Here's a probability weighting function. It maps probabilities p to the weights pi of p, and this is a linear probability weighting function. Yeah, that's the probability weighting function implied by expected utility. It just maps. So we could put in 1 here. Actually, I don't want to do that. You can see the point. This is what. Okay, that's not what Kahneman and Tversky in 1979 think the probability weighting function is supposed to look like. That's what Tversky and Kahneman in 1992 think that the probability weighting function is supposed to look like, and that's what we typically that's what behavioral economists sort of fall back on. And in that 1992 paper that's in the non-required readings for Tuesday's lecture, there's actually a mathematical, an analytical function that gets you that curve. So what's going on here? Suppose you have, here's 0.01, let's say.